In this session, we are going to understand one of the most important geometric concepts in engineering graphics, conic sections. From bridges and cooling towers to headlights and satellite systems, conics are everywhere in real-world engineering. So let's begin from the very foundation, the geometry of a cone. A cone is a three-dimensional surface generated by the rotation of a straight line. One end of this line remains fixed at a point, called the apex. The other end moves along a closed curve. As the straight line rotates, it forms the curved surface of the cone. This simple rotational motion creates a powerful geometric shape, used widely in engineering design. Now let us clearly understand the important parts of a cone. The apex or vertex is the topmost fixed point. The axis is the imaginary straight line joining the apex to the center of the base. The generator is the straight line that rotates to generate the surface of the cone, and finally, the base is the closed curve along which the generator moves. These elements are fundamental for constructing and analyzing conic sections. Now let us understand how conic sections are formed. When a plane cuts a cone at different inclinations, different curves are produced, such as circle, ellipse, parabola, and hyperbola. So, the angle of the cutting plane determines the curve. Let us observe the standard sectional cases. If the plane is parallel to the base, we get a circle. When the cutting plane passes through generators, if it is inclined but not parallel to the generator, an ellipse is formed. When the plane is parallel to the end generator, the section is a parabola. When the plane is parallel to the axis, also if the plane cuts both naps of the cone, it produces a hyperbola. These are the fundamental geometric conditions defining each conic. Now, let us define conics mathematically by using eccentricity. It is denoted by E. Is the ratio of distance of a moving point from the focus to distance of the same point from the directrix. This constant ratio classifies the curve. For an ellipse, E is less than 1. For a parabola, E equals 1. For a hyperbola, E is greater than 1. Eccentricity is the key parameter distinguishing conic sections. Now observe the geometric construction concept. Every conic is defined using axis, vertex, focus, directrix. The ratio of distance from focus to distance from directrix remains constant. That constant ratio is eccentricity. This focus directrix principle is the foundation for engineering constructions. Let us connect theory to real engineering practice. An ellipse is used in arches, bridges, dams, and elliptical gears. A parabola is used in suspension bridges, headlights, and solar concentrators because it reflects parallel rays efficiently. A hyperbola is used in cooling towers, hydraulic channels, and radar antennas. Conic sections are structural, optical, and aerodynamic solutions in engineering. Real-life applications of conic curves. Now observe how conics appear in daily life. Elliptical paths, defined planetary orbits, and athletic tracks. Parabolic shapes are used in dish antennas, telescopes, and mirrors in lasers. Hyperbolic profiles are used in cooling towers and advanced communication systems. Conic curves are not abstract mathematics. They power real-world technology. Finally, let us look at construction methods. Ellipse, parabola, and hyperbola can be drawn using various methods are given below. In the upcoming videos, we will systematically learn how to construct these curves using the eccentricity method in a precise academic and professional manner. In this